when we're starting to think about setting up a database, one of the most important things that we need to do is to try and strike this balance about how much data do I actually need in order to get started. Do I really need to delay the whole process of going out there and doing it because of doing my due diligence? Can I get started? And I also wanted to spend a little bit of time talking about database construction, because I see some horrific databases out there. And my first database, as I said, was in 1988, and I still see people making the same mistakes in terms of database creation in 2011 that I saw in 1988, which I kind of find amazing, but there we are. This database is going to become one of your most valuable sources of knowledge. Get that in your head from day one. This is going to be one of my most valuable sources of knowledge. Okay? If I have a valuable source of knowledge, wouldn't it be nice if I could use it? Wouldn't it be nice if I could find my information in there? And I see so many databases around the world which have been so badly constructed that you just can't find anything. You can't get to that valuable, useful information. And I'm not saying that the database design is bad or the software is bad, so I don't need the vibration people to get the hackles up. I'm saying the way it's been set up is bad. Some software is just a list, and it's just a big long list of things, and you can hide a list in a variety of different ways, but when you look deeply enough you see it's still just a list. Whereas some software actually has a tree structure with as many as say 6 levels in it. So certainly the equipment that I tend to work with, I've got 5 levels in my tree structure to get me to a measurement. So from describing a part of the plant down to a measurement, I've got 5 different levels in which I can lay that out. And that can be useful, especially if I don't have to use all 5. Most important problems that people get wrong in terms of databases. Number 1, in fact, number 1, 2, and 3 in the top 10. Consistency. If you're going to plan a database so that at some point in the future you're going to search through it, consistency is critical. If I name something in a certain way, I must name all things the same way. Because if I don't get the same answer. And in most software packages, this also allows us to have the differences between uppercase and lowercase. So if I put something in uppercase and I put the same thing in lowercase, it's not the same thing. To the human, it's the same thing, but to the computer system, it's not. And we can use that to our advantage if we want to, very, very nicely. We ought to be able to structure a database in such a way that the structure of the database and the surveys that we carry out, the work orders, if you like, to go out and take readings, don't need to be the same. If I think, for example, of a conveyor, or if I think, for example, of a paper mill or something of that nature, certainly a conveyor is an easy one to think about. I'll have 100 roles on that conveyor. My database is going to be set up role 1, role 2, role 3. Role 1, drive end, non-drive end, operator side, free side, however you want to call it. But it's going to be set up role 1, role 2, role 3, role 4. Is that the way I want to take the data? No. Because I'm going to go down one side and then climb underneath or climb over the top, and then I'm going to come back up the other side, right? So my database needs to be constructed role 1, role 2, role 3. But my survey will be 1, 2, 3, 4, 5, 6, 7, 7, 6, 5, 4, 3, 2, 1. So I need to make sure that I have a system, and if I'm at the point of investigating the purchase of a system, now's a good time to ask awkward questions like, is my tree structure separate from my survey structure? Are they independent? Can I have a machine exist in more than one survey? Can I have a weekly survey and a monthly survey? Can I have an operation A and a process B survey that include the same machine? It's useful stuff to have. It's also useful sometimes to actually be able to assign operations, to assign measurements, even to assign data collection processes to a specific person. Bill is the competent engineer for doing the steam trap survey. So the only person that can load the steam trap survey and go out and do the steam trap survey is Bill. That's a useful thing to be able to do. Brief, very, very simple example about database creation and logic. Now, splitting a database down into sensible, practical work areas, zones, for want of a better word to use. And within a zone, I might have a number of fans and pumps and so on. So do I have a consistent naming system for those? Sometimes the naming system that I have is the naming system that's in the CMMS, or it's the naming system that's in SAP, but that doesn't go deeply enough. Does everybody call bearings outboard, inboard? Or does somebody call them drive side, non-drive side, or drive end, non-drive end? And does everybody call them the same? And what are you going to call them? And make sure that everybody knows what they are called. These are important things. Very important things. So you need to get those right at an early stage in the system. Measurement intervals. One of the key points about relying on taking data on a routine basis is that I need to be able to ensure that that data is actually being collected routinely. If I'm relying on data being collected on a monthly basis, I want to be able to manage that. I want to be able to see what's overdue, to see what's not being done. So I need to be able to look in my database and I need to be able to find that out. I need to be able to create a database to take multiple measurements. We've already talked about things other than just ultrasound. We've talked about the need for measuring temperature. When you talk about going on and thinking about lubrication, somebody said yesterday something that I disagreed with, that the most important parameter in greasing and lubrication is viscosity. That's actually technically not correct. In my mind, it's one of three things that's important. You need to worry about the viscosity and control that. You also need to understand load, and you need to understand speed. And when we teach the level 2 ultrasound course, we spend quite a bit of time talking about the physics of lubrication. And it's the combination of the three things, speed, load, and viscosity, which is actually the key to the success of lubrication. So, how can I successfully lubricate a bearing without having a good understanding of its speed and load conditions? So sometimes there's other data I need than just ultrasound, because my ultrasound signal is going to vary with speed sometimes, depending upon how my conditions are changing. When I'm working with my database, I need to be able to edit. I need to be able to move. I need to have the facility to move things around. I need to have the ability to take data that's not in my survey. So you're out in the field, going around doing your normal bit. Somebody calls you over and says, Tom, can you just have a listen to this? Yeah, sure. So you go and have a listen to that, but where does that data go? That's valuable information. You can't just throw it away. You have to be able to manage that. Data which is not part of the normal day-to-day survey that you're out doing, where does it go? How do you manage it? How is your software going to deal with that? How is your instrument going to deal with that? These are big questions. Alarms. Alarms are very, very useful. I was not so keen on alarms earlier on, if you remember, when I said it was 9.995 an alarm, yes or no. But they are good indicators, and there's a variety of different ways in which you can use alarms. Most people only use alarms in terms of, or even visualize alarms, in terms of absolutes. The level is higher than this, the level is higher than this, the level is higher than this. And that's okay, that's fine. And they're very useful. But there are other types of alarms that are also useful. So let's think about safe alarms. I can use safe alarms as an indicator of a good reading, or I can use a safe alarm as an indication of a problem. Let's think about our steam traps, for example. If I have a safe alarm, if I have a low safe alarm set at 50 degrees, 80 degrees, really, it doesn't matter. And if I measure the temperature on this steam trap and it's 45 degrees, I can use my system to generate an alarm there and then, right in front of the operator's eyes, that says this temperature is below expectation. In other words, it's probably blocked. The steam trap is probably blocked. The line is probably dead. But the operator is now no longer going around in moron mode. This seems to be one of these old-style marketing hype goals, wasn't it? That you could use a trained gorilla to take readings. I'd rather use somebody that's actually competent and aware, if you don't mind. Thank you very much. And I'd rather give them the tools to become even more competent and even more aware. But that's making it complicated. No, it's not. It's making it useful. There's a slight subtle difference there. So safe alarms I can use as an indicator of something being too low a level, too high a level. Maybe even it's a bad reading. But another very interesting set of alarms that are quite useful are relative alarms. Relative alarms being a case where I look at the reading that I've just taken and I compare it with, for example, the previous reading. Or I can compare it with some absolute gold standard. And I can, again, create an alarm that says this is so many dB higher than before or so many dB lower than before. Downward going alarms are also very, very important. In many cases, when you start thinking about bearings, for example, there's always a calm before the storm, or frequently a calm before the storm. A bearing will go worse and worse and worse and worse and worse, and then it suddenly gets better. No, it doesn't. That's the final death throw. And if you don't trap that dip, then you say it's okay, and then it fails next week. And whose fault is that? Yours. So having downward going alarms is also very, very useful because it gives you a means of trapping something which is in the very final stages of failure. And you can say, this has gone down, okay, fine. Has anybody done anything about this? And then when everybody says no, then you know that, well, you're about to, because it's in its final stages. When we deal about greasing, for example, we use this relative when we teach people about on-condition lubrication, and we use a very simple thing of 8/16/24 as a decibel change. So 8 dB increase above the previous reading or a baseline reading, consider greasing the bearing. 16 dB above that, there's probably some early stage damage there. 24 dB and higher, there's most definitely some damage there. Now, if you have an instrument where you can actually embed those alarms, and this is what I was saying to Chad earlier when he asked the question about unconditioned lubrication. If I have an instrument where I can embed those alarms, I can actually send the greaser out and tell the greaser, you're taking these readings, and when the yellow light goes on, you grease that bearing. And if there's no yellow light, you keep moving. Yeah. So all the technology is embedded. You know, I like to think of it in terms of a swan. You see a swan floating across the surface, and it's beautiful and it's elegant and it's sleek, and you never see the little legs go underneath. You just see this elegance as it goes across. That's the way your database system and your data collection and everything should be. It should be nice and smooth and nice and easy and pretty, easy to work with for the people who are out working with it. And all the difficult stuff is buried. It's buried underneath. You don't need it. You don't need to know that it's this frequency and that number and all the rest. It's important that it's set up correctly, but once it's done, the operator just goes out and uses it with confidence. So I can find alarms very, very useful. If I've got alarms that I can use out in the field, I can find them even more useful. And I can have alarms that overlap. So it's not an absolute alarm, but it's a relative alarm. And I can set alarms which are even tied into logic trees. So I can have a logic tree. So for example, we post on our website a logic tree for doing steam trap surveys. And within that logic tree, you've got things like, is the temperature high? Yes, no. Well, I can use my alarm system in my equipment and in my software to deal with that question. And I can set up an alarm for that yes, no. Another interesting thing, and I mentioned it before, is uppercase and lowercase. And having a consistent nomenclature for how you actually structure these things. So a very simple example, I use capital first letters, uppercase first letters, for proper names. So an ID fan would be a capital I, capital D, capital F. A wastewater extraction pump would be a capital P. And within that, so that's a proper name, that's a machine, but that machine is comprised of components. So that machine would have a motor and a fan. It would have a motor and a pump. And they would be lowercase. Having a system set up like that, and that really, I think you'll agree, that's a very, very simple way of working. A simple thing to think about. But now, when I come to doing my database searching, if I do a search on a fan capital F, then I will pick up the fan bearings and the motors. But if I do a search for a lowercase f, I'll only pick up the fan bearings. Or a lowercase p, I would only pick up the pump bearings. So if I want to start doing comparisons, if I want to start doing statistics, if I want to start refining my alarms, if I want to start doing all sorts of improvement, again, don't forget, improvement. We don't want to get to a plateau. We want to get better and better and better. So if I want to do improvement, one of the things I want to do in my improvements is to be able to tighten up my alarms, to make my alarms, for example, more statistically relevant. So I want to be able to look at my valuable database and to extract data. That's not... Is that too big a question to ask? To be able to look at a database and extract data? I don't think that's a big question to ask. Try it. And see how difficult it is. In many cases, databases are there for you to use. They are not there for you to extract data. And there are companies that actually specialize in you can buy products simply that will help you in that data mining process. Well, that's great for them, but wouldn't it be nice if the system you bought in the first place was designed properly so you could do your own data mining? We talk about surveys in our world of ultrasound. We talk about surveys, not routes or routes. And really a survey is it's a work order. Go and take readings on. Go and do this. It's a work order. It's nothing more sophisticated than that. As I mentioned before, it's nice if I can actually get to a situation where a machine can exist in more than one work order. So I can have a monthly survey, I can have a 3-monthly survey, I can have a process survey that would all call up an individual machine. But I don't want to necessarily take data on it 3 times, so I want to be able to also have a system where I can track what's been measured and then create conditional surveys. A conditional survey would be a compression of a survey that would take all the data that should be in the survey and remove everything that you've already done, everything that's not due, because you've already got that data, so you can shrink that down then to just what's left to be done. No phones, please. And the order of my measurements is very, very important. So when you're going out and setting up surveys, strongly recommend you walk them first. I see so many times people have set up surveys and the person who set up the survey has clearly never set foot in the plant. And he doesn't know that you've got to get a certain size step ladder to get to a certain place. He doesn't know that you've got to open 3 gates and knock 3 times and ask for Cyril in order to get into a certain place. And you have, and the way that the survey's been set up, you've got to do that 10 times rather than once. So walk them before you code them, so that you know you've got something that's sensible and makes sense and is easy to follow through. If you make this task too difficult, it won't get done. Don't have day-long surveys. Don't even have half-day surveys. Most working days have natural breaks, don't they? You come in, you've got morning break, you've got lunch, you've got afternoon break, you've got home. Normally there's 4 typically in a day. You set jobs across those, nobody likes to do them. Create surveys maybe that are on, you've got people out there who can do your survey work, but they're too busy. They're too busy to give you a day. They're too busy to give you half a day. Okay, have some surveys that are just an hour long. Have some surveys maybe that are even just half an hour long. Maybe the little ones are actually a treat. You've been good today. Here, go and do that survey. Does that sound funny to people? Yeah, I can see a few people laughing there, because it's supposed to be a boring, onerous, drudging data collection task. Doesn't have to be. It can be a treat. You're out. You're out taking readings. Go on, get lost. Oh, thanks. It'll get done that way. You got any readings to do? But you don't hear that very often, do you? Got any readings to do? Why not? We often want to take dynamic data as well. We've talked about the reasons why we want to take that dynamic data. In ultrasound, we take that in the time domain, because the large majority of problems that we're trying to identify are short duration, random, non-periodic signals. And all these things break the rules of Fourier's mathematics. So if you just go straight and take a reading and store it as a spectrum, the large majority of the information that you want will actually not be there. And in previous reliability web events and previous conferences, I've presented papers before where I've shown time signals that are completely and utterly different, and yet the spectra are virtually identical, because it breaks the rules. So when you're dealing with random events, short duration events, things of this nature, transient signals, working with the spectrum is a bad move. And most of the data you want isn't there. It's in the time signal. So be aware of that. The other thing to be aware of, which is a slightly more technical thing, is that when we capture our ultrasound signal, we heterodyne the signal. I see a lot of stuff in articles and writing about heterodyning or demodulation. That's elephant or kangaroo. That's about as close as those two technologies are to each other, or those two processes are to each other. We heterodyne. Heterodyning, the process of heterodyning, we don't have time to talk about it today, but it's well documented. The process of heterodyning throws out harmonic signals. So looking at data with a harmonic cursor, you're unlikely to find it unless you're very lucky, freakily lucky, because the majority of the data you're looking for will be there as sidebands. So you'll still keep the frequency data, but if you look at with a harmonic cursor, it's not there. But if you look at the same data in the spectrum with sideband cursors, you'll find it. So again, it's a fundamental mistake that people sometimes make, is that they're looking at the data with the wrong cursor and they don't see. So a couple of things that we go through, again, these are level 1, level 2 things, but worthwhile highlighting at this stage. Again, it's worthwhile remembering the swan and saying, wouldn't it be nice if I don't need to worry about setting sampling frequencies and frequency ranges and all these things? Wouldn't it be nice if that's all done for me? And all I have to do is specify a length. Well, actually, wouldn't it be even better if I don't even need to specify the length? I can just go out and take a reading of whatever length I want, and that's it, done with. Everything else is dealt with. No reason why that can't be done. Absolutely no reason. Is taking a static measurement any more complicated than taking a dynamic measurement? No. It's a push of a button. That's it. Push the button, done. How complicated a measurement was that? I just pushed the button. So was it static, dynamic? Push the button. So you can send anyone out to take as sophisticated the data as you like, because all they're doing is pushing the button. And they're also listening to the signal as they're going around, which is, again, the great advantage. So this is the kind of typical example of a tree-structured database that you can get. So you can look at data, you can look at your time signals, you can look at and even play your time signals, so that you've captured a signal, brought it back into your computer, you can analyze it in your computer, but you can also just play it. And better still, you can export it from your database as a WAV file, so you can email it to somebody else to play it. This sounds strange to me. What do you think? Isn't that nice? Simple. Very simple things. You can put alarms on all of these things as well, so you can have traffic lights that change from green to yellow to red. You can even have a counter which tells you how many things are in what condition. So all of these things can be there just in front of your eyes if you need it. So you've got the counter there of how many points are in alarm. And you can have survey lists detailing all the different points, the order that they're in and everything else, and it's completely separate from the database. But the database, the data management, the stored data, and the diagnostics are all in one place. It's not multiple software for doing different bits and pieces. It's all together in one place. So, again, whether I'm doing static, whether I'm doing dynamic, doesn't matter. It's all in the same place. Is this a steam survey? Is this a valve inspection? Is this a bearing? Is this electrical? Doesn't matter. It's all in the same place. I push the same button. I just go through the data in the list of the survey in exactly the same way. The simplicity is the real key to the success. What do I see on the screen? I can see simple things like this on the screen. I've got my tree structure, what sensor I'm supposed to be using, because that's important. I can even have embedded alarms. I can see what my alarm is. I can have messages, pop-up list of messages. So Again, one of the things, if you've got someone out taking data, when I have people out taking data for me, one of the key things I tell them is, you are my eyes and my ears. I'm not there to see that there's an oil leak. I'm not there to see that the belt's are frayed. I'm not there to hear there's a strange noise. You have to tell me. And you either have to do this in a written form, or you have a messaging system inside your instrument that allows you to do that for you. And that's your eyes and ears. Dynamically, it's just a case of specifying the length of the signal. 1 second, 3 seconds, 60 seconds, whatever you need to actually capture sufficient data. We have one customer who's capturing 300 seconds in a single event because he needs 5 minutes. The whole cycle is 5 minutes long. So what point is giving somebody 20 milliseconds worth of data when you have a 300-second event? That's completely and utterly useless. He has a 300-second event. He needs 300 seconds worth of data. The end. That's all I want. Simple. You'd think. Not really. It's actually quite difficult. But it's achievable. I want to start off now on communication. What's the objective of reporting? What's the objective of reporting? I would say to you that the objective of a report is to inform the people who need to be aware of what they need to do to bring their asset back to the best condition. That's what I would say to you. In other words, your job is a translator. The machine, the valve, the pump, the transformer, whatever it may be, it's talking to you. It's talking to you in an ultrasonic language that you understand. And your job is to translate what the asset is telling you into meaningful information that the planner, the repairer, whoever it may be, can work on. That's your job. That is what a report should be. What are time signals and spectra? Normally just hieroglyphics. I could have written the whole thing in Sanskrit for all the use it would be, for all the information that it would have actually transferred in terms of meaningful data. What should a report be? Again, I would suggest to you, a report should be the product of a considered engineering opinion based upon the facts that you have gathered. What should it not be? Spewed out list of numbers. How many times do I see reports? Does your software produce reports? Oh yeah, you just go, and it spews out numbers. Great. What do they mean? That's your report. But what does it mean? Is that useful? No. What should it be? What should a report be? It should be considered opinion. It should be engineering fact. I believe you have a problem on this machine, on this valve, on this pump, this bushing, on this transformer. You need to do this. That's a report. Not 30 pages of numbers. That's not a report. What are the key points I need to get across? What's the problem? What sort of problem is it? And most important, and I think a very useful and very powerful thing to include in reporting, is the consequence of do nothing. You can leave this alone, but right now it's a $500 fix. But you can leave it alone. It'll be a $50,000 fix. Now you know that when you're writing the report, so why don't you put it down? Is it politically incorrect to state the blindingly obvious? Shouldn't be. Shouldn't be. So, run through some different types of reports. What do I need to include? If I'm going to do an air leak report, then I need to identify where the leak is. I need to maybe tag it if I can't fix it. I need to document it in such a way. Why can I not fix it there and then? Well, normally, I can't fix it there and then because maybe I haven't got the part, or maybe because I have to turn the air off in order to fix it. Okay, fine. So you turn the air off. Where's the leak? Well, it's where the tag is. No, it's not. Well, how are you going to fix? You must have meant that. So, if you're going to write a report to fix air leaks, and the only reason that you're writing the report is because you have to turn the air off, make sure that your report is written with sufficient detail that someone will be able to find the leak with the air off, and will be able to find the part that needs to be fixed with the air off. Otherwise, everybody's wasting their time. There's nothing worse than being told there's a problem but not being told what the problem is. I had a car like that once. Very, very annoying. It used to tell me that they had a problem, but it couldn't tell me what the problem was. And it couldn't tell me where the problem was, but it said, there's a problem. There's nothing worse than that. I'd rather the don't know condition. Don't tell me if you don't know, because there's no point in me knowing. There's 2 piles of leaks. Which would you prefer, gents and ladies? The first pile of leak or the second pile of leaks? And how are you going to get from one to the other? Tagging, documentation. I've been to places, and I'm sure you've got places. I've been to places where I've been out with an instrument and found an air leak and said, what's that green tag there? Oh, that's this year's air leak survey. Oh, great. Okay, so we're in agreement then. What's the blue tag? That's last year's air leak survey. Okay, so you've got the factory dressed up looking like a Christmas tree. Wonderful. Are you saving any money yet? No. Famous quote from a guy called Dan Durbin, former chief engineer at Anheuser-Busch. 17 plants, I think he was responsible for. 17 systems all out there finding air leaks eventually. But it was a slow start. It was only after a while when the CFO realized that there was actually money to be made from this that it actually happened. But finding leaks doesn't save a penny. You have to fix them. You have to fix them. Steam trap surveys. First few times, this is going to be a big, big list, because if you've never done a steam trap survey, you probably have lots of defective steam traps. So you've got lots of things that you probably need to fix. One of the interesting things, of course, with some of your steam trap problems is, can I correlate a steam trap problem with a production problem? We can't maintain heat in the oven. We can't maintain temperature in the autoclave. Well, if you can track that back to a specific steam trap, this is very useful in terms of your do-nothing calculation. The do-nothing, if you don't fix the steam trap, is that we still can't operate properly. So we need to do something about it. There's a lot more planning required in the repair process here, because I need to think about how am I going to do it in terms of what do I need to shut down. Big issues. Big reports required as well, with lots and lots of data. There are some simple things as well that you need to include in there, like I don't know how many times I've found people who have themselves then found steam traps that have been installed the wrong way round. So the arrow, the direction of flow, very useful, but it's still been put in the wrong way round. And then they're troubled with the steam trap doesn't work properly. Really? valve inspections, another big one. Not all the valves are going to be working on any one day. So if you just have a big survey that says go out and inspect valves, you're only going to get some of them. So again, this idea of having localized surveys or having the ability to compress surveys is useful. We've already discussed the basic problems are just blocked, passing and cavitating. 3 very, very simple things to deal with. Trending is going to be very useful here, and I'm going to show you in the last quarter a very nice example of that. No, I'm not. I'm going to show you now. Sorry. Here's an example of a valve. The black line was taken upstream, the yellow line was taken downstream, but the blue line there is actually with a contact probe measurement taken on the valve stem itself. And here we have the nominally closed position, and here we have the apparently, according to the computer, 10% open position. And the difference there between those two, 25 dB microvolt. Well, 26 dB would have been a 20-fold difference. 25 is about an 18 dB, an 18 times difference. So the actual voltage measurement that I'm getting in the 10% cracked open is 18 times higher approximately than in the nominally closed position. I think that makes it a relatively sensitive system for detecting 10% or even 5% open. Electrical surveys, try and keep this managed along with your infrared. You've got one guy going around with the infrared camera, empower him to do the ultrasound as well. As I said, best practice from a safety point of view is that before you open any cabinet doors, you have a listen anyway. Well, that's great. Now, on some of the high voltage stuff, you might want to be doing trending and you might want to be doing analysis. But on the low voltage stuff, you're really doing binary things. Is there tracking? Is there arcing? Yes, no. When I'm doing the high voltage stuff, of course, I don't want to be nearby. So I can listen to it, and I can use a parabolic dish to make it very easy for me to listen to the ultrasound. But I still need to document it. Guess what? You're not going to be tagging this, are you? Not at 400 kV. You're not going to be out there with your silly little tag. You're not. So make sure you've got a decent camera. Yeah. Which bushing is it? Well, it's that one that's about the 47th pixel in there, but you can't quite see it because it's a bit of a blur. Not really useful. So make sure you've got a decent camera with a decent zoom so you can actually photograph that individual bushing. Simple things. I'm a bit of a geek. You may or may not have noticed. I randomly will stop at the side of a road if I see a small substation somewhere. And if I've got the time, you can see what's coming up, can't you? I'll randomly stop at the side of a road, and if I've got 10 minutes, I'll leap out, open the trunk, get out my equipment, and have a listen. I am a geek. Well, gents, the interesting thing is I am currently 5 for 7. Out of 7 random stops, I now have found problems on 5 substations. Just random. I wanted to show you a nice example here of find it, fix it, check it. Here's a very nice example of a well-documented case study that you'll find at sdthearmore.com of an application on some transformers. And here you see a before and after. So here in the before time signal, this was before cleaning. There were 3 phases, 3 problems. After cleaning, 2 of the problems absolutely went away. There was nothing left. But this third one still had some residual tracking associated. So yes, we've cleaned it, but the problem hasn't completely gone away. So we're not having total faith in the cleaning. We're actually coming back and doing the find it, fix it, check it. I was actually doing a level 1 training course in a power station in Canada a couple of years ago, and they had a 380 kV transformer in the car park just outside the training room. So as part of the training course, we went outside and had a listen, and this transformer had just come back from cleaning. It had only come back from cleaning about a month prior, and lo and behold, it still had some corona on it. So my cost of being there as a trainer was already recovered by day 2 of the training course, because they had a transformer which had just been boxed off, brought back into service, and was supposed to go for another 2 years, that still had corona on it. So it was never going to do that. So, lubrication, again, we can think in terms of find and fix, and we can think in terms of planned. Find and fixed, as a report, is beautiful. We've been out, we've checked so many bearings, we found that this number needed greasing, we've greased those, and in the database we have the before ultrasound signals, and we have the after ultrasound signals, and it's completely finished. Job done. Other way of doing it is planned. You go out, you take the readings, you generate a report that says these bearings are high, and then using that report, you then create a next work order which says go out and grease just these bearings, not the rest, just these bearings.